So scales of measurement. Remember, the magnitude or the amplitude of a sine wave can be expressed by reference to its sound pressure in newtons per square meter, also known as pascals. Most of the time, the magnitude of the sine wave is described in decibels, and decibel notation requires an understanding of logs and antilogs. So, antilogs, they're pretty basic to understand. When you see something that says antilog 2, 2, basically all you have to do is solve the problem. So 2 squared, or 2 to the third, or 10 to the second, or 10 to the third. In this example, 2 is the base, 2 and 3 are the exponent, 10 is the base, 2 and 3 are the exponent. And then you just solve the problem. So 2 squared is 4, 2 to the third is 8, and so on. So thus, antilog xn equals the base to whatever value in the exponent. In this example, it would be 10 to the 1.7. You could use a scientific calculator to solve these problems. Now, scales of measurement. The word measurement describes a process whereby numerals are assigned to objects according to specific rules. Numerals are symbols that act as labels. For example, Roman numerals. A numeral cannot be added or subtracted. A number is a symbol with a fixed relationship to other symbols. Numbers can be added and subtracted. There are 4 scales of measurement: a nominal scale, an ordinal scale, interval, and ratio. Each scale of measurement becomes more and more powerful. A nominal scale, things are either the same or the different. So, for example, if we were in your typical speech pathology graduate class, we could count the number of males to the number of females, simply counting one group versus the other. You can't do anything in a nominal scale of measurement other than count. An ordinal scale of measurement is more powerful. Things are more or less than each other. So we know that in an ordinal scale of measurement, A is greater than B, B is greater than C, C is greater than D, and so on. The problem with an ordinal scale is that we don't know by how much A is greater than B, or B is greater than C, or C is greater than D. There's no fixed relationship between the numbers. So the letters are not numbers. They can't be added, or they can't be subtracted. Even if the letters were replaced by numerals and we gave them values like A equals 4, B equals 3, C equals 2, D equals F, we still can't do anything with them in this scale of measurement. For example, if you wanted to play a competitive golf match with 4 different people and you assign them numerals, let's say B is way better than R and D is also really great and C is really bad, and you think, oh, I can even them out by putting B with S or D with R. That's not the case because you don't know the exact value between each of them. So in our first scale, the nominal scale, you're either one or the other. You can't add or subtract. The ordinal scale, we know something is greater than something else, but we don't know by how much. We can also not add or subtract. So though it's more powerful than a nominal scale of measurement, it's not the most powerful scale out there. An interval or a linear scale is what you're most comfortable with or most familiar with. That's our counting scale. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a fixed relationship between each of them in our counting scale. 1 and 2 is 1, 2 and 3 is 1, 3 and 4 is 1. If I were to count 2, 4, 6, 8, 10, what would be the relationship? 2. There's a base, and you keep adding or subtracting by the base. So the size of the interval between the adjacent numbers is a constant, and the side of the interval is called the base. We're familiar with the base of 1 in our scale, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 5, 10, 15, 20. In this case, the base would be 5. And here are some other examples of bases in the scale. Then you find the interval side. Because we know the base is a constant, we know that 4 exceeds 3 by 1, and therefore, and so on, so that we can actually add and subtract and do a lot of powerful things with an interval scale of measurement. With an interval scale of measurement, we can say that one object is different from another, that one object is more or less than another, and, for certain, the number of units more or less than one is from the other. The ratio scale is also called the exponential scale or the logarithmic scale. And this scale is important for hearing. So this is an exponential scale. When I say exponential, you can think of the expression like the size grew exponentially. With a ratio scale, we have an absolute zero. The principal characteristic is that one unit on the scale is so many times greater or less than another. So you multiply or you divide the base, whereas with the linear scale, you're either adding or subtracting from the base. With the ratio scale, you're multiplying or dividing by the base. So if the base is 1 times 1 times 1 times 1, you just get 1. If the base is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and so on and so forth. If you were to use 10 as your base, look at how quickly it grows. So 10, 100, 1,000, 10,000, 100,000. So it's growing exponentially, if you've heard of that expression. It means it's growing very, very fast, because with a ratio scale, also known as an exponent scale or a logarithmic scale, you're taking the base and you're multiplying it or dividing it. If the exponent is a 0, the base to 0 equals 1. That's a rule that you should remember. If the exponent is 1, the answer is equal to the base. So 2 to the 0 is 1. 2 to the first is 2, and so on and so forth. In this case, the base is 3. So a base is x, the exponent is n. So you have the base, and the exponent tells you how many times you multiply the base by itself. 2 to the 5th power means you multiply the base 5 times. And here are 2 examples of a base at 2 and a base at 10. Remember, a number to the 0 equals 1, regardless of the number, and a number to the 1st power will always equal that base number.